Welcome. My name is Ron Papa Schmidt, and I'm the creator of the Net Zero Now YouTube channel. This is going to be video 4C. It's going to be part of the science overview section. And in this session, we're going to talk about the structure and operations of Earth's climate system. This will also be a foundational core video. So let's begin. So in this presentation, what I'm going to do, a quick recap of video 3, Why Now? In that video, we talked about why we need to get the net zero greenhouse gases now or as fast as humanly possible. And I want to talk about the structure of Earth's 5 spheres of its climate system. And those are the atmosphere, the hydrosphere, as you can see there. And we'll go through each one of those. And then we'll just talk briefly about what are the subsystems that make those up, what are the tipping points for their subsystems if they have tipping points or tipping ranges. And then we'll just sort of take a look at all of that together, sort of what does that tell us when we if we look at all of the spheres together at their tipping points, and then we'll make some final observations. This is 4C, so we did 4A and 4B. 4B talks about tipping points, feedback loops, and cascading feedback loops from a climate science perspective. So if you've not watched that video, and if you're not familiar with those terms and how they work in the climate space, I would highly suggest you watch that video first before you watch this one. Okay, so what's the objective here? Why should you watch this video? Well, first of all, this is going to be long, just because of the very nature of the subject, and I want to you sort of have to cover it all in one video. Second of all, it's going to be a little bit scientific and detailed oriented, so that may not be for everybody. I understand that. I would guess if that's the case, why don't you try to sort of, if you could, tough it through this video. I'm not expecting you to remember anything here or to really understand how these things work. I just want you to get maybe a feel for how things fit together, get an appreciation for how interactive these various different subspheres are, and sort of really where we're at from a science perspective or status of those systems right now, because I don't think most people really understand that. And I don't hear anybody really talking about it in that frame. Even if you're a climate skeptic or if you're the most advocate person for believe that we have a climate crisis, nobody seems to talk about it and look at it from this perspective. So I want you to get an appreciation for that. So that's what I'm trying to get accomplished here, okay? So let's begin. Okay, so here's video 3. You can see the thumbnail for it in the upper right-hand corner. And basically, we could summarize that video in the table below. And what it said was that 1.5 degrees Celsius or 59.2 degrees Fahrenheit, that's where we're at the end of 24. You will see significant environmental, economic, and social impacts. And I think just take a look at what's happened in 2025. Okay, we began the year with the Palisades fires. Or in about June or July, we had the flooding occurring in Texas. One day we had, I think, in the United States, over 700 tornadoes and another 35 people died. And when I'm recording this is just a couple of days after Melissa sort of went through Haiti, Jamaica, and parts of Cuba, and just basically just substantial damage to them. And that was sort of, I think, close to the highest or the most intense hurricane recorded in history, if I've got that correctly. So you can clearly see that there's been significant social and economic impact. I look at all the forest fires and everything else that's occurred so far in 2025. What the scientists said here was that when we got to 2 degrees Celsius or 60.1 degrees Fahrenheit, which will be somewhere we're saying between 2034, maybe 2032, less than 10 years from now, okay, the world will see catastrophic and likely irreversible damage. Well, the catastrophic is pretty obvious. So if you remember what happened in 10 years ago in 2014 compared to where we were in 2024-25, look at how much more damaging weather has caused and the problems we've had from weather and higher temperatures on Earth. I mean, right now, probably 10, 15%, almost of every single night's newscast on ABC, NBC, CBS, everyone you want to watch, is talking about weather. I mean, just never happened 10 years ago. And so this is saying, well, 10 years in the future, look at how much has occurred in that 10 years. Well, it's going to get a lot worse in the next 10 years. So seeing catastrophic damage is pretty obvious, I think. Irreversible is not. I mean, that says there's maybe nothing humans can do to change what's going to happen and lead to the higher temperatures we see below that. I think once you get through this video and you see how Earth's climate systems operate and where we're at in terms of the tipping points and with those different climate systems, I think you may get an appreciation for that. And that's what I want you to get out of this video today. So let's begin. Here are the 5 spheres: the atmosphere, which is air; hydrosphere, which is water; cryosphere, which is ice; the lithosphere is the surface of the Earth and the mantle underneath it; and the biosphere is where living things live. But it could be either on land or in the ocean. So we're going to take each one of these. So we'll start with the atmosphere. And the atmosphere, if you take a look at the table below, we'll have this similar table for everything. So I'll just cover the structure of the table. First, we'll identify the subsystem. Then we'll identify whether that subsystem has a tipping point or not. And if it does have a tipping point, what is a tipping range? And then for systems without tipping points, are they being impacted by weather? And if they do have a tipping point, we'll probably have a comment in terms of are we seeing some impact already in terms of weather or higher temperatures, I should say. Now, if you take a look at those, we talk about clouds, thunderstorms, etc., and we talked about what's driving that is that for every 1 degree increase in temperature Fahrenheit, you get 4% more moisture into the atmosphere. And more moisture leads to more clouds. More clouds lead to more thunderstorms, tornadoes, cyclones, atmospheric rivers, etc. Not only more, but I mean more intense. And we explain all of that in video 11, where we talk about extreme weather, thunderstorms, tornadoes, and cyclones. So I'm not going to cover that anymore. I want to just talk for a little bit about the jet stream, because one of the things I want to do is just give you a flavor for each one of these spheres. What happens, give you a sense of the dynamics going on there. So let's talk about the jet stream real quick. And I want to just start real quickly with this diagram here on the right, and that's where we show the average temperatures of what's happening on Earth. And you can see the average temperature, all of them are increasing, but the temperatures are increasing faster over land than they are in the ocean, and are increasing fastest in the Arctic. And that's also borne by this heat map that you see on the left-hand side. If you look at the very top, you can see how dark it is, and if you look at the chart below, it sort of would tell you that, okay, it looks like in the last 50 years, the temperature of the Arctic has gone up about 7.2 degrees Fahrenheit, much hotter than the rest of the Earth. So that leads to then atmospheric circulation, which is probably the primary driver of our weather that we experience here on Earth. Now, let me say that I've covered that in much more detail in 2 presentations. You can see the thumbnails for them below, 10A and 10B. So I'm not going to cover that here, so you can check those out to really get a better understanding of this. Well, let's make a couple of quick points here. If you take a look at this illustration on the left-hand side, if you look towards the equator, you quickly see something called the Hadley cell. And if you take a look at the Hadley cell, what do you notice? You see a red arrow pointing up to the troposphere, and then sort of this bluish arrow going up towards the Horst latitude and then down. That is the circulation pattern of the wind at that point in time. And you see the ferrule cell, you can see the same kind of thing occurring, only it's occurring in reverse. And then you see the polar cell, a similar thing. So those cells and those wind patterns are really driven by a couple of things. And some of the things we don't really see, we know happen, but we don't really, what am I trying to say? I guess I'm trying to say we don't really experience it or sense it when we're outside just looking at the sky. And that is that the Earth is orbiting around the sun at 67,000 miles per hour, and to us it seems like we're standing still, right? At the same time, we're spinning around our axis at 1,000 miles an hour, and we're in a Milky Way, which is moving at 1.3 million miles an hour, okay? And then the other thing that sort of influences our temperature, there are many more other than these, but some of the really important ones here, is that the Earth is tilted, and therefore that's what causes our seasons, because we have longer periods of sunshine than we at different times of the year. Well, what's happened, okay, remember the graph we just talked about, how the temperature is rising much faster at the pole than it is at the equator. Well, these circulations you see in the Hadley cell, the ferrule cell, the polar cell, etc., are driven by temperature differential. So as the temperature differential between the Arctic and the equator decrease, that affects the speed with which these things operate. And that has a fairly major effect. So let's get to the jet stream. The jet stream, or in this illustration, sometimes they call it the polar jet, okay? And if you look at the illustration on the upper left-hand corner here, you'll see the polar jet there. It sort of rides between the polar cell and the ferrule cell. So what's happening? As we said, in the Arctic, the temperatures are warming faster than they are in the poles, so the temperature decrease, so the temperature difference is decreasing, okay? What that does is that weakens the jet stream, and that causes the jet stream to then meander. If you look down below at the illustration below, you can see how the jet stream is just meandering up and down. You can also see the Arctic warming amplification, and then you can also see this sort of this brownish kind of color again, or tan color, the big H for an atmospheric block or high system that sort of stays in one place for a while. So because the jet stream is weaker, that means these high pressure systems stay in place longer in a particular location. What does that mean? Well, that's why, now we're getting, a lot of times when we get rainstorms and other kinds of things, they last much longer. You also notice that we get heat waves, they last longer. That is because the jet stream is slowing down, and therefore it holds the high pressure system in place longer. Now, sometimes that can actually be beneficial. Okay, remember we just experienced Melissa and all the damage that it caused. Fortunately for the United States, the jet stream meandering happened to hold a high pressure system just off the coast of Florida. And because of that high pressure system, as the hurricane was forming and moving from Africa towards the Caribbean, etc., it was forced upward by the westerly winds we saw in that previous graph. But it never reached the United States. If that high pressure system hadn't been there, what would have happened is that would have continued to go from east to west, I'm trying to say, and probably would have landed up in the Gulf of Mexico. And if it did that, then the westerlies would have carried it up through the United States, and this massive hurricane would have caused just substantial damage to the United States. In fact, it might even become more intense because of the water's so warm in the Gulf. So, it's just not a one-way effect. That's what I'm trying to say here. In addition, the other thing that's happening, though, is this meandering is now taking warm air from the Gulf and moving it up into the Arctic. So what's that doing? Well, that's further decreasing the temperature differential, right? The other thing is happening in reverse. Sometimes it takes cold air and pulls it from the Arctic down further. Remember in the last couple of years where all of a sudden we're seeing really freezing conditions sometimes in Texas and some Florida and some other places? That's because of the meandering jet stream. And the other thing that sort of happens is you get a longer area of where you have cold and warm fronts in tension. That leads to more extreme weather. So that's just a quick overview of the jet stream. I will do a separate presentation on just the jet stream itself. But we're at the infancy of this website, and so I mean, not website, I should say a YouTube channel. So we haven't created a lot of those videos yet. So let's get to the hydrosphere. This is water. One interesting thing here, let's just talk about this. I found this fascinating. Is that the scientists are telling us they don't believe the level of water has changed on Earth in the last 4 million years. A billion years, I should say. It's just changing shapes, okay? Sometimes more of it's in the atmosphere, sometimes more of it's as water, sometimes more of it's as ice. Either, it could be on land and glaciers or other things, or sea ice or whatever. And sometimes more of it's in lakes and things like that. But really, it stays the same. Now, one thing, this is something I was not aware of until I sort of got into this client space. There's something called the global thermohaline circulation, or THC, and it has three major components we identified here, the AMOC, the SPG, and the SOC. Now, they all have tipping points, and it turns out that the AMOC is already in the very beginning of its tipping range, and the SPG is a little bit further into its tipping range. And the SOC rather is that's the area around Antarctica, and there just hasn't been a lot of research done down there yet. And so we know there are tipping ranges, we just don't know what they are yet. So let me just real quickly talk about this. Again, I'm going to be doing separate detailed presentations on a lot of the things you see here. We just haven't gotten that far yet in the development of this YouTube channel. But if you see this global circulation, you see two things. You see sort of a tannish, orangish color and a greenish, bluish color. So the tan, orangish kind of color is really the AMOC riding on the surface of the ocean. And then it goes down, sinks down to the bottom, goes down the bottom of the ocean, and if you take a look at the top here, you see the SPG up there, and the top of the AMOC. It goes down, it goes to the bottom of the ocean there, and flows down to Antarctica, where it sort of upwells and comes back up and starts riding on the surface again. And it's a massive amount of water, a massive current, okay? That turns out to be fairly important, because what happens is all this water mixes. So right now, it takes about 1,000 years, they say, for the water to complete its complete cycle. So what that means is a lot of the carbon dioxide and other things we've generated since the Industrial Revolution that's been sitting on the surface of the ocean gets dragged down to the bottom of the ocean, and fresher, less polluted water gets brought to the surface. So that has a beneficial effect there. It also mixes all the sediments of these these oceans, which is also very healthy. And it also transfers heat. So what would cause it to go down? What causes it to go down is the water. Water is salty, particularly in the Caribbean and other kinds of things. So as it moves further north and it starts to evaporate, if we're looking at the AMOC here, what happens is as the water evaporates, salt stays in the water, so salt doesn't evaporate. So the water gets denser, saltier. And as it continues to go up and gets colder, it gets denser and denser, and that weight sort of drives the water to the bottom of the ocean. That's what drives, that's the engine of it. So again, I'll do separate sessions on those. And then in addition to that, we also have these gyres, which are more surface-related kinds of circular patterns of water. And you can see there are 5 major gyres here. Let me just talk quickly about the AMOC. If you take a look at the graph on the right, you can see the North Atlantic gyre, and you can see how that's where, if you see that's one of the things. You also have wind patterns going the same way, but that's where the hot air and things from Africa get blown over, start moving over the Caribbean, over the Atlantic Ocean towards the Caribbean Sea and the Gulf. And if those thunderstorms start occurring there, and then if they in turn sort of gather around a core or an eye, you can create huge tropical storms there. And then what happens is they get sort of, depending on what the weather conditions are like, where they hit the westerlies, they sort of then move up towards Greenland, up the coast of the United States towards Greenland, and eventually over to Ireland and Great Britain and the Scandinavian countries. So we show the picture of the AMOC, we show the Gulf Stream. Actually, the Gulf Stream, it runs between the AMOC and the coast of the United States. But basically, you almost think of them as one constant stream, but they're not. And so what basically happens is, one of the things that happens here is it transfers massive amounts of heat. So if you take a look at the left-hand side, the upper graph, there's a heat map. See how red that water is in the Caribbean and in the Gulf of Mexico, and along as it starts going up the coast of the United States? So what happens is the AMOC takes that, moves it up the coast of the United States, and then around Newfoundland sort of starts moving it over towards Europe. And it's really it's Ireland, Northern Ireland, the British Isles, the Scandinavian countries, okay? Now, one other interesting thing, if you take a look at a globe, take a look at sort of the Scandinavian countries and where they are from a latitude perspective. Now you look over to Canada and you see you're in northern Canada, sort of Yukon country, right? You look over to Russia and you say, hey, wait a minute, this is pretty close to Siberia. Those are so much colder. Why is in this area, the temperature so much warmer? The reason is because of the AMOC. It's transferring this massive amount of heat from the Caribbean and other things over to those areas. So what happens if the AMOC slows down? First of all, it is, and you can see evidence of that because the clients say, when you see a cold blob, that's that blue in the middle slide, that's that sort of blue area, heat map area up there. When this cold blob starts forming, that tells you that the AMOC is slowing down. They have other measures also. So what's going to happen real quickly with that is then that all of a sudden, as it slows down, the water in the Gulf and other kinds of things along the United States is going to get hotter. It's going to rise, and so you'll get more surge. When we have major storms, you get more surge damage. The other thing that's going to happen is that the temperatures in the Scandinavian countries and et cetera are going to drop dramatically. And one other side effect of that is, since the southern part of Europe is getting increasingly hotter, you're going to see increasing temperature differentials between those two, which leads to much more extreme storms. So again, that's real quick. I don't really expect you to remember much of that from that quick explanation. Again, we'll do more videos on that to talk about it in much greater detail if you're interested. But I just want to get you a sense of, okay, this thing is going on. If the AMOC slows down, it really has some significant implications. It would also reduce the amount of greenhouse gases that are on the surface of the ocean and are being driven down to the bottom of the ocean too. So let's move on. Let's go to the cryosphere. Now, if you take a look at the cryosphere here, you look at all the subsystems, you can see that they all have tipping points. The only ones that don't, where I have regionally variable, would be sea ice and glaciers. Each one of these glaciers and each sea ice has a tipping point, okay? But they're all located in different parts of the globe, and so we don't really have a universal tipping point for them like we would for Greenland or Antarctica, etc. So I just showed them as regionally variable, but that doesn't mean they don't have tipping points. And then look at the current status. You can see that most of them have either are in their tipping range of partially tipping or showing some significant impact. Now, Greenland happens to be in its tipping range, and I think the consensus is that it's already tipping. The Atlantic West, the WAIS, which is the West Antarctic ice sheet, is in its tipping range. There's some evidence that's tipping. In fact, there's a major glacier there called the Thwaites Glacier, which I sometimes called the Doomsday Glacier, which they're projecting is going to fall into the ocean probably within the next 2 to 3 years. And then you see the status of these other items. I talked about this extensively. I used the Greenland as an example of how it tips and things like that in video 4B. So I'm not going to cover that again. So let's move on to the lithosphere. And again, I'm just going to run through this real quickly because the lithosphere doesn't really have tipping points. What it really is, it doesn't impact our climate when an event occurs. An event would be a volcanic eruption, a major earthquake, and then you can sometimes have tsunamis that occur as a result of that. So since they're more event-driven and in the interest of keeping this video to a reasonable amount of time, I'm just going to move forward. Now we get to the biosphere. And the biosphere, here are the major subsystems there, the Amazon rainforest. Now you can see the Amazon rainforest is close to tipping. It should tip within the next 10 years probably. That's probably true of other tropical rainforests. The boreal forest is already in its tipping range, and we're already seeing some impact. But because the boreal forest is massive and it has some parts of it have lower temperatures than other parts. So what I'm trying to suggest is some parts are further south. The most northern portions are much colder than the southern portion of the boreal forest. So that's what I'm really trying to say here, okay? But you can see some evidence of it already tipping. We have a lot of forest fires that are starting to occur in those areas. And then we have the temperate forest. And again, for savannas and drylands and lakes, they all have tipping points, okay? But there's so many of them, and they all are in different latitudes and other kinds of things. So it's hard to come up with a universal tipping point. So I just showed those as regionally variable. And lakes are even more localized than that, so I just say highly localized. But many of the lakes are already being significantly impacted by higher temperatures. And then we have the warm water coral reefs, which are already in the tipping zones, and you can see a number of them are already starting to die out. So let me just real quickly cover the Amazon. And again, for each one of these, I will probably do an additional video. For sure, I will do one on the Amazon. And I've talked about that a little bit, what happens here in video 4B. So I'm just going to try to cover this in a minute or two. One of the things is we know the Amazon rainforest is shrinking. And one of the graphs, if you take a look at the graph on the right-hand side there, what they did is they said based in 1970, the size of it then, where are we now? And they sort of measure where we are. So it's right now it's just above, it's a little bit more than 80% of the original size it was in 1970. But you can see it's steadily moving down. Now, when you get to the 80% to 75% range, that's when they say the Amazon rainforest could probably just tip, and there's nothing we can do to really stop it. What's the main driver here? Deforestation, okay? Why the negative impact? Well, what happens is, so right now it's a massive carbon sink. So as you deforest, you cut down trees, right? So they're no longer pulling carbon out of the air. The other thing that happens, we replace it with agricultural activity, particularly raising cattle, that generates significant amount of greenhouse gases. And then you have the trees you cut down as they're a huge reserve of carbon. So as they get burnt or whatever we do with them, they also release additional carbon dioxide into the atmosphere. That's all, I think, pretty obvious to everybody. Let me tell you one thing that may not be so obvious, is that because of the size of the Amazon rainforest, and you can see it if you look at the illustration in the upper left-hand corner there, just how massive it is, it sort of generates its own weather. Why? Well, because you have all these trees there, and they go through this process called transpiration, where they generate, as part of the living process, water vapor into the air. That water vapor in the air adds to a denser cloud system within the Amazon rainforest, which in turn generates more rain. Well, if as we cut down the size of the rainforest, you have less area there for the transpiration to occur. So if once we get to a critical point, it's going to start slowing down. That will in turn raise temperatures of the area. There'll be less rainfall, and the whole thing will just continue to cycle. Again, we'll have videos to talk about that in much greater depth. So let's just take a look at where we're at. So we talked about all 5 spheres, and we talked about their tipping points, or where they don't have a tipping point. We covered that again in 4B. They still can be impacted by weather. And so what I did is in light blue, I took the systems without tipping points. Mostly a lot of those occur in the atmosphere. But they are being impacted by weather, so we know that. And then I took the areas that are sort of regionally variable that we know of also. While we don't have specific single tipping points for those, we know they're already being impacted. We know sea ice around the world, glaciers around the world are melting at fast pace. We know that lakes are, etc. We know all this stuff's happening. Okay. And so I showed that in this sort of a bluish color. And then in red, I went and said, so we know today we're at 1.5 degrees Celsius. So what systems today then are already in their tipping range? And where that's true, I identified those in red. And then in green, I said, okay, well, so we think within the next 10 years, for sure, we'll reach 2 degrees Celsius. And so there'll be some more systems that will tip. So what systems will tip at 2 degrees? So I listed those, I illustrated those in green. Now, if you just take it back and look at that, and so the black is those that are above 2 degrees Celsius. Just step back and look at that. There's very little black. All of these things are almost in their tipping ranges or something, are already tipping. And, if you remember when we talked in the video, we went through the example of 2B, where we went through the example of cascading feedback loops. Well, all these things start cascading one another. They influence one another. They'll just speed up the process. So if you look at that, it's a frightening thing. So you can easily see, okay, I understand now by just looking at this visually why this could be an irreversible process. What is a human being going to do to slow down, to speed up the AMOC? It's a massive system. How about Greenland or Antarctica? So if you look at those things, that's why I'm concerned. That's why I think the statement that within the next 10 years, the world will not only see catastrophic things, but likely see irreversible damage. Look at when this stuff's going to happen. So let's wrap this up. I summarized that information in this little table here. So if you look at it in blue, these are the systems with no tipping point, but are already being impacted, or those that are regionally variable and are being impacted. And so we have 12 subsystems there. That represents 44%, I should say, of the 27 subsystems we've identified. Now we have another 8 that should be tipping that have already hit their tipping range. So that gets us to 74% of Earth's subsystems are already being impacted by or in their tipping range today. Now, if we go within the next 10 years, we'll add another 4. That brings it to another 15%. That means 89% of Earth's subsystems will be within their tipping range. That's kind of frightening. Which leads me to one of my other things. You know, I love my Eagles songs and their song titles. They just speak to me. They have another song out there with this great title. It's called Failed Grasp of the Big Picture. And I have to say, I haven't seen anybody that I've talked to or otherwise that really sort of looks at it this way and thinks about it this way. I mean, even the most advocate person who are true believers in the danger of higher temperatures, they don't talk about this. And I think that's for 95, 99% of the people on Earth just aren't looking at this appropriately. I mean, the title just says it all. It's a failed grasp of the big picture, folks. We live in this planet. It has spheres. It has subsystems. They all have tipping points. There are cascading feedback loops. All that stuff's happening, folks. So, let me wrap it there. So what can we do? Well, we can vote, subscribe to this channel. We need to start talking about it, too, with people. We need to get people to understand what's really going on here. Because we have to do something, as we talk so passionately about in video 3. And let me just, again, just say this. You know, I know these things seem pessimistic, but fundamentally I'm an optimist, or I wouldn't be doing these presentations. And I think the problem that we have is people don't understand the problem. If human beings understand this problem, if we get rid of our political bickering or the whatever you want to call the junk that's going on about we don't have a climate crisis, etc., all we have to do is agree, and I think, and get committed to working together to solving the problem. I mean, we're an incredibly creative species, but we're running out of time. Okay, I mean, we have kicked this can down the road so long that we are literally almost out of road. So with that, I say thank you for listening. Please get involved and do something for the sake of your kids, your grandkids, and yourself. And please watch some of our other videos. Again, thank you for giving us the time.